one giant planet, almost 95 times the mass of our Earth, with a radius 9.5 times greater. A ring system, more than 280,000 kilometers in diameter, almost the distance from the Earth to the Moon, and yet so thin, a few tens of meters. At more than 60 satellites, with an extraordinary variety of shapes, sizes and compositions. Even the slightest speck of dust interacts with every part of this system in an unceasing ballet, governed by the force of gravity and by energy exchanges over billions of years. The force of gravity decreases with distance. So for all the planet's satellites, the side facing the planet is attracted more than the opposite side. This phenomenon, called the tidal effect, is accompanied by a loss of energy in the form of heat and also modifies the orbits of the bodies involved. In the case of Saturn, mutually opposing tides exerted by both the planet and the satellites progressively extend the size of their orbits and make them more circular. Since the middle of the 17th century, astronomers have observed and recorded the motion of the satellites of Saturn. Today, using this extensive record of observations, the international team Encelade has reconstructed the orbital evolution of 4 of the 8 main satellites of Saturn. The big surprise is that the observations indicate that the rate of slowing of this orbital evolution is more than 10 times greater than that predicted by theory. To understand the consequences of such a result, let's pay a visit to the surface of a very special moon, Enceladus. A ball of ice and rock around 500 kilometers in diameter, Enceladus is situated 238,000 kilometers from Saturn. Its elliptical orbit means that it is subjected to intense tidal effects from the giant planet. The resulting deformation and heating of the interior of the satellite is such that it generates huge geysers that eject ice particles and water vapor from its south pole. Until now, calculations indicated that these tidal effects would only last for a short time, because the ellipticity of the orbit of Enceladus must decrease as its interior heats up. The geysers would then disappear, but they are still there and have been regularly observed during the Cassini mission, a collaboration between the European and American space agencies since 2004. Why? Based on the new calculations, with at least 10 times more energy being dissipated in Saturn due to the orbital motion of the satellite, the astrophysicists of the Encelade team have been able to show that Enceladus may be in a state of equilibrium, heat loss by the geysers being offset by the energy due to tidal interactions with Saturn and by the gravitational action of its neighboring satellite, Dione. Returning to the orbital motion of the satellites of Saturn, tidal effects decrease sharply as the satellites move away from the planet. But what is the origin of this extreme slowing of the orbital motion? Traditionally, energy balance calculations do not take into account the presence of a core inside the planet, assuming it to be an inert mass. But in reality, Saturn is composed of a large gaseous envelope surrounding a central core composed of rocky and icy components, and its mass could reach 18 times that of the Earth. The Encelade team embarked on modeling the energy dissipation produced by this rocky core. The tidal effects of a rocky Saturnian core amplified by a gaseous envelope combined with tides in this gaseous region can reproduce both the orbital evolution of the satellites and the internal heating of Enceladus. But then a new problem arises. If the positions of the satellites are recalculated with this new model, we find that they should be much farther away than they are today. Everything seems to indicate that the satellites we see today are younger than the planet and have not had enough time to get away completely. And this is another result that forces us to rethink the Saturnian system in depth, or to change our conception of the formation of satellites. Originally, the grains of ice and dust that make up the rings orbited in a disordered way around the giant planet. In a very short time, just a few years at most, they spread to form the disk we know today. But recent simulations of the dynamics of the rings made within the Encelade team show that small satellites can form at the outer edge of the rings. The researchers believe that in the past, the rings of Saturn could have been much more massive and very different from those of today, leading to the formation of satellites progressively over the course of the evolution of the solar system. Detailed calculations show how this naturally explains the current size distribution and position of almost all the icy satellites of Saturn. This new formation scenario is quickly reinforced by a strong argument. It was long known that the masses of the Saturnian satellites located up to the orbit of Titan increase with increasing distance from the planet. However, this observation comes as a natural consequence of the mechanism of the formation of the satellites. Indeed, the rings of Saturn become less massive as they form new bodies. Such as new satellites are created, their masses become progressively smaller. So now, if we take into account this new mechanism as well as the new value for the dissipation of tidal energy in Saturn, we obtain satellites that are in the same positions as they are today. We now have a scenario consistent with observation that not only tells us much about the formation of the satellites of Saturn, but also about the story of the solar system itself. Understanding the Saturnian system provides a better understanding not only of the evolution of other gas giants in our solar system, but also the evolution of extrasolar planets. And since at the moment, most of those that have revealed themselves to us are gas giants, like Saturn, they could also harbor a rich and fascinating ecosystem of rings and satellites.